Gnanam Paramam Dheyam. Knowledge is supreme.
Welcome back. So far we have seen uh, that given any piece of equipment, how do we go about identifying what are the control variables, what are the manipulated variables, and what is the uh, final architecture or structure of the control system. Even though we did not formally see how do we screen which is the best alternative out of all the possible options, a lot of times heuristics are used, or you go with what is the prior experience, and sometimes there are some techniques which we will be looking when we talk about multivariable control. So at the end of this synthesis problem, what you have is a number of different controllers, and each of those controllers, especially the our domain of within the domain of this particular course, we will have so at the end of this synthesis problem, we have these different controlled variables, and then we have mapped them to a particular input. So, this within the context of multi-loop CISO strategy. Now, a disclaimer is that it is not necessary that this is the best architecture you can go with. Lot of times this is what happens at a regulatory level or the bottom level, and you would typically have these individual controllers which are implemented at the very base level of a control system. So, once you have all this structure, the next question which we have to ask is, what type of controller is this? Is this P, PI or PID? Because again this is the domain or this is where we are going to restrict ourselves. If you want to really generalize this particular problem, selection problem, it will be in addition to that, are we going to use any advanced control strategy? Is it going to be a linear, non-linear controller? Is it going to be an optimization based controller? So, all those sort of questions come in this synthesis problem. Selection problem. So, for this course we will be dealing with whether it is P, PI or PID. So, in order to answer this particular question, we have to use some rules of thumb, and which are based on some analysis which we have already done when we talked about the performance of PID controller. So, when we talk, so let us look at all these PID controllers, and that will help us formulate this rule of thumb strategy. So, when you say P control or the proportional control, the main advantage is it is very simple. There is only one variable Kc which you have to decide. It is oftentimes very fast. It is a fast action. It does based on the current error. It is going to take out the give you the action. On the other hand, when we talk about the limitation, is that cannot get rid of upset. So, that is a very main limitation of a P controller. Then we go to proportional integral control. So, the advantage of a PI controller is that you get offset free response, but this comes at the cost of sluggish or slower dynamics. we have seen that a PI controller increases the order of the system, so the response of the system becomes slower or sluggish. And then lastly, we have looked at the full blown PID controller, proportional integral derivative control. The advantage is it can improve speed of response. But at the same time, it has limitations in terms of can react to measurement noise, which is a very key thing. It may destabilize the process, and difficult to tune. This is the last tuning problem, that means finding the best value of Kc, tau and tau d. It is like the controller is having three particular angles which we have to different directions in which it has to optimize. So, it becomes a difficult problem to select the best values of Kc, tau and tau d. So, based on this, the rule of thumb strategy is as far as possible try to use a P controller or a proportional controller, and that means if your offset is acceptable, then always you would try to go with a P type of a proportional controller because it is fast. If the offset is not acceptable, then you have to go with either PI or PID controller. So, the demarcation between PI and PID is that if the inherent process itself is fast, then having an integral action on top of that is going to slow it down, but not to a very bad or not to a very great extent. So, the combined PI effect on a very fast process may still be acceptable, and so when offset is undesirable and the system is fast, you will go with a PI type of a controller. And then if the inherent system itself is very slow or a multi-capacity process and you want to get offset free response, then having a PI controller will slow it down even further. So, in order to improve the speed of response, you would go with a PID controller. So, we will try to use this rule of thumb to different types of control variables which are possible in our chemical engineering plants. And again, a disclaimer is that these are rules of thumb. This is what on an average or majority of the cases how these controllers would be, and wherever possible I will try to give you some exceptions as to where this rule does not apply. So, we will start with the very commonly used controlled variable, that is a flow control. So, if you try to recollect the example which we had about the inline blending, there were two options, two CISO options. So, one of those was this controller 1 requires you to control the outlet flow. So, this is a flow controller. So, if this is the controller which we want to design further, then what type of a controller we have to use. So, as it turns out, flow dynamics are typically fast. And mostly you want to set a particular flow going to a piece of equipment. So, if it is a raw material flow, you want a certain flow rate going into the system. If it is a product flow, again you want a certain product to be delivered to the customer. So, mostly offset free response is desirable. So, based on our rule of thumb, when I say offset free response is desirable, it narrows down to two types of controllers, PI and PID, and as the dynamics are fast, PI becomes the typical choice. So lot of times when you see a flow controller in a chemical plant, you will see that it will have a PI controller. Now there are two exceptions to this rule. So one is a flow as secondary control objective. In cascade strategy. Now we have not seen what is a cascade control so far, but it is a control strategy where there are two control loops which are connected together. One is a primary control loop and other is a secondary control loop. So when flow is a part of this secondary control loop, typically offset is not that critical and offset is tolerable. So in such a case, as in order to improve the speed of response, you may have a flow as a proportional control. On the other hand, sometimes this flow is also part of a multi-capacity process. So an example is shown here. You can see that this is the bottom of the reboiler, and we are trying to control the flow of steam which is going to go to the reboiler. This is a condensate, this is known as a condensate throttle reboiler, also known as a flooded reboiler, where the amount of steam which goes into the reboiler is controlled by the amount of heat transfer which is going to happen. So the way this particular reboiler works is that you have this condensate flow. So as steam condenses after giving heat, you try to control this flow of steam going into the system by changing this liquid valve. So when you open this valve, the amount of condensate, the level of the condensate goes down. As the level goes down, there is more area available for heat transfer, so more amount of steam will come in. So that is how this steam flow is controlled by using this particular valve. And what you can see is this is a very multi-capacity process. When you open this valve, it is first going to change this liquid flow. As you change the liquid flow, it is going to change the level. Once that level changes, the amount of area for heat transfer changes. This changes the way the steam condenses, and once steam condenses, this pressure goes down, so more steam is going to come in. So it's a fairly multi-capacity process. It's a very slow process. So in such a case, the flow controller will actually be a PID controller. So depending, so majority of that, just to summarize flow control, majority of the times it will be a PI controller. When it is part of a cascade control and a secondary control objective, it will be a P controller. If it is a multi-capacity process like a flooded reboiler, then it will be a PID controller. Now let us see how the control loop will look like. So you have a pump which is going to deliver this flow. So there are two ways in which this flow controller can be implemented. One is simply having a valve at the outlet. So you will measure the flow and then accordingly change the valve opening. If the flow is higher than the set point, you will close the valve opening. So what it does is it changes the resistance across which this pump has to do the work. So more is the resistance, less will be the flow through the pump. So it works on that particular principle of the pump. The other way you can control this flow, which has some inbuilt safety, is having a recirculation loop. So in this case, you will measure the flow and accordingly change how much fluid recirculates. So here the total amount of flow which goes through the pump is sort of remains the same, and what you do is depending on what is the requirement, you recirculate more amount of the fluid. So this particular strategy has is going to have more power consumption, because the amount of work which is the amount of flow which goes through the pump is higher. You also require a bigger pump. However, it has an advantage that it will ensure that the pump always has certain minimum amount of flow ensured through the recycle. So this way it will try to avoid the low flow regime of the pump and avoid cavitation and all those kind of mechanical and any mechanical issues arising out of low flow. So this is more robust, or it is more it has inherent safety built into it, but it will result in higher cost of operation. So these are the two simple ways in which flow controller can be implemented, control strategy can be implemented, and most of the times it will be a PI type of a controller. Let us now look at the level control. So level control is typically, as you recall the example of the flash vessel, in this case we had implemented level controller not as a primary control objective, but typically it is a secondary control objective. Because you want to do some inventory control. You want to maintain a certain inventory of liquid in that particular vessel so that it does not go dry or it does not overflow. So lot of times offset may be acceptable. So lot of the cases when you have a level controller, you are okay with the offset and you want a fast response, so the proportional controller is quite common. For level control. So if you look at the example of the surge tank, what we had, if you look at the example of the flash vessel, you will have a, will measure the level, and very commonly you would try to control it by changing the outlet flow. So that is how a level controller will be implemented in a process. A lot of times you try to look at what is the outlet flow from that particular vessel, and then try to control the level by using that particular flow. Next we go to pressure control. So similar to level, pressure control is also implemented as a secondary control objective. To maintain vapor inventory. So offset may be desirable or may be acceptable. So mostly it is a proportional controller. So a lot of times you would have a pressure control as a proportional controller. So if we see the example of a surge tank, what we had, so you would have a pressure measurement, and it's very so sometimes you would have the outlet flow which is which is manipulated to control the pressure, but it is quite common that you also have some way to tie in the inlet flow as well. So, this is from a safety perspective, and what we end up having is a single pressure controller which is going to manipulate both these valves. This type of control strategy is known as a split range control, and we will see the split range control in more detail in the next week. So, most of the times pressure will be a proportional controller, and there are two exceptions to this. One is, and both these are around distillation top pressure control. So, in distillation, pressure plays a very key role. Apart from maintaining certain inventory of vapor inside the column, pressure also affects the vapor liquid equilibrium between these species. So, the extent of separation, which is characterized by relative degree, relative volatility, it is a strong function of pressure for many systems, especially when you talk about vapor vacuum distillation. You are talking about very low pressure, and relative volatility is very sensitive to the pressure. So, in that case, even a small offset may change the performance of the column. So, in that case, offset may not be acceptable. So, vacuum distillation may not be acceptable. So, that means we have to either use PI or PID control. So, again, depending on the type of distillation column, we may have PI or PID control. So, I will give you two examples, both are industrially relevant examples. So, when you talk about air separation, what you are going to get at the top of this column is nitrogen, which is gas. So, the way you can control the pressure inside this column is by simply measuring the pressure and accordingly changing this valve opening. So, this is a very fast dynamics. So, you can use a PI control. Now, this PI controller was possible because we did not have any condenser here, and the vapor is the product at the top. The other type of, or a more conventional distillation, is that you get vapor at the top, then you condense the vapor, and then the reflux goes back. So, in this case, the way you control this particular pressure is that the handle which you have to control the pressure is this coolant condenser duty. So, if the pressure inside the column is high, that means the vapor there, the enough number of vapors are not condensing. So, you have to increase the condenser duty, so that more vapor will condense and the vapor inventory will go down and the pressure will also go down. So, here it is a multi-capacity process. The moment you change this coolant flow, it is going to change the amount of, when you change the valve, it is going to change the flow of the coolant. It is going to change how much the heat transfer inside this condenser, how much vapor is condensing. Once that amount of vapor condenses, it is going to change the material balance at the top of the column, and the pressure is going to show its effect. So, it is a fairly multi-capacity process. So, we will have to use a PID controller here. So, having said that, every distillation pressure controller will not be a PID controller, because you also have to weigh in about the offset, whether the offset is acceptable or not. Lot of times high pressure distillation, small offset in pressure is not going to affect the extent of separation. So, you may even go with a simple P controller. Next, we go to temperature control. So, temperature Most of the times temperature is controlled because you want to maintain a certain temperature inside a reactor, so which is favoring the kinetics of the desired product. So typically offset is not desirable. So you have two options, one is PI or PID, and again we try to follow similar rules. If the inherent process is fast, you will try to go with a PI controller. If the inherent process is slow or multi-capacity, then we will go with a PID controller. A lot of times we have the heating or cooling done through a jacket, so it becomes a multi-capacity process. So if I draw a reactor which is steam is providing the heating, so it is a endothermic process, and we want to control the temperature inside this reactor. So we want to control the temperature by changing the steam flow. So when you change the steam flow, it is first it is going to change the amount of steam going into the jacket, then it will change the jacket temperature, and then eventually it will change the reactor temperature. So it's a fairly multi-capacity process, and then most of the times this temperature controller will be a PID controller. And then the last type of variable which we commonly want to control, and I would say we want to control, is the composition control. And the reason I am saying want to control is a lot of times you will see that you will not see a composition controller as a PID controller per se. So mostly it is the primary control objective. Offset is typically not acceptable. So you would typically want to think that it will be a PI or a PID controller, and what happens is composition measurement is typically very slow. And if we go back to our stability analysis lecture, you will see that the moment you have some sort of a measurement delay, it is going to severely restrict the amount of controller gain which you can put into that system, and it eventually results into a very slower or poor performance of the controller. So because of that, even though composition is a primary control variable, you will rarely see that composition is controlled as a PID controller. What you do is something known as the inferential control. So you try to infer the composition through a secondary controlled variable and most of the times this is a temperature control. So even though we want to control a particular composition of a particular stream, we would not directly have a composition controller, but we will have a temperature controller which will ensure that if the process runs at that particular temperature, the composition control will be ensured, and the composition control in that case would be part of a higher level controller also known as a supervisory controller. So let me explain that through an example. So we had this splitter, we had this flash vessel, so in this particular vessel I said that we want to maintain a certain bottom's purity, but we would not have a composition controller per se. What we would be doing is we would have a primary temperature we will have a temperature controller which is going to manipulate the amount of heating or steam which goes into this particular vessel, and with the assumption that if I maintain this particular temperature, because of the vapor liquid equilibrium and having ensured that there is also a pressure controller, having maintained the particular pressure at, if I maintain that particular temperature, I can ensure that the corresponding composition is also maintained, and then this is how indirectly we will control composition. And in order to make this foolproof, what you will also have is a secondary controller which is going to measure composition. So, we will have a composition controller and it is going to give the set point to this temperature. So, even though this particular temperature controller is trying to ensure this xb is equal to xb set, if there is some error in terms of the VLE, or the system is not behaving exactly as per that VLE, or there is some unidentified component, what this additional controller will do is it will try to change this set point of the temperature controller, fine tuning of that temperature, so that you ensure the desired product quality. This would typically be a supervisory controller. So, with this we have analyzed all different types of variables which you would see in any chemical plant, and we have seen typically how each of those control loops will be, whether in terms of P proportional controller, PI controller, or a PID controller, and in terms of composition controller, mostly it will be some sort of a model based supervisory controller. It will rarely be a PID controller. So, we will take a break here, and when we come back we will look at, having now decided the type of a controller, how do we go about selecting the best values of controller parameters, that is the controller gain, integral time constant, and the derivative time constant. Thank you.